to a lecture series on linear algebra. In this lecture, we are going to see a result on linear dependence and independence, and we will work out problems based on this result. Let us get into the theorem. Here, suppose if you are taking some elements from the vector space, these elements are either linearly independent or out of these elements, some elements are linearly independent and some element is a linear combination of the preceding elements. This is what we are going to prove in this lecture. Let us get into the proof. Suppose these vectors are linearly independent, then we don't have anything to prove, right? So why we are taking it as linearly independent? If we are taking a collection of vectors from a particular vector space, it has only two possibilities. Either that collection of vectors put together in a set is going to be linearly independent set or linearly dependent. Suppose I am taking that as linearly independent, then there is nothing to prove, right? So we are done with the proof. Even in this statement they have given that we have to prove either they are linearly independent or something is going to happen of this form, right? Suppose v1, v2, etc. vn are not linearly independent, okay, and consider alpha 1 v1 plus alpha 2 v2 till alpha n vn is 0. Here what is going to happen? Not all alpha i's are 0, right? Since they are assumed to be not linearly independent, this is true, okay? If I consider this to be equation 1, this is true when not all alpha i's are 0, okay, because they are assumed to be not linearly independent, that is linearly dependent, okay. In this case, let alpha k be the largest value, okay, be the sum value such that this alpha k not equals 0, right? Which means what? After that, before that all those values are not 0, okay. After that there are many elements which are going to be 0, right? Here what has actually happened is alpha 1 v1 plus alpha 2 v2, and it is going this alpha k vk plus alpha k plus 1 vk plus 1, and it is going till alpha n vn, which is 0. Here what we are assuming is that these entries here, these alphas are non-zero, the 0 values, not all 0, which means there may be some 0 possibility, right? Out of that, all those I am writing in the right side, rightmost side. So these entries are 0, okay. Now here what I can do is that I can consider these things. Then what you will have is that alpha 1 v1 plus alpha 2 v2, and it goes till alpha k vk is 0. This is what you are going to get, right? So in this case, let me have only this in this side, that is alpha k vk alone. Let me have it in one side, because all those entries, this linear combination is going to give you a single vector. You can operate the inverse of that vector on both sides, so you will get what? Alpha k vk to be the minus times of alpha 1 v1 plus alpha 2 v2, and it goes till alpha k minus 1 vk minus 1, right? Now if I operate the multiplicative inverse of this alpha k, because it is assumed to be non-zero, the multiplicative inverse exists, so I am applying that on both sides. So I will have what? Vk to be minus alpha k inverse alpha 1 v1 alpha 2 v2, and it goes till alpha k minus 1 vk minus 1, right? So this is going to be the case. Now I can multiply all those things inside using the distributivity of the scalars that is present in the vector spaces, right? So this is going to be minus alpha k inverse alpha 1 v1 plus minus alpha k inverse alpha 2 v2, and it goes till minus alpha k inverse alpha k minus 1 vk minus 1. Now you will have to examine what this is. See, here these alphas are, where are these alphas from? All those alphas are taken from the field F. Okay, whenever you take an entry from a field F and suppose this is non-zero, this implies your alpha K inverse is also in F. Okay, now you have two entries in F. By the closure property of F, since F is a field, this is a member of F. Similarly, this is a member of F. This is a member of F. So along with the vectors, what do you have? You have some element of F, which clearly tells you that your Vk is a linear combination of the preceding elements, that is V1, V2, etc. till Vk minus 1. Right? So this completes the proof of this results. Now, to illustrate the theorem that we have seen, let us consider these examples in R3 of R. Okay, here the first set of vectors is this. Let me check whether this is a linearly independent set or not. For which, let me choose the scalars to be x, y, z in R, such that what I am writing is that x times of 1, 1, 1 plus y times of 2, 3, 4 plus z times of 3, 5, 6 and is to be equated to 0, 0, 0. So this is going to give me what? X plus 2y plus 3z, x plus 3y plus 5z, x plus 4y plus 6z and is equated to 0, 0, 0. So when we have this, let us put that in a matrix form. Okay, it is going to be 1, 2, 3, 1, 3, 5, 1, 4, 6. Since this is a homogeneous system, if you equate, you will have a homogeneous system of 3 unknowns and 3 equations, right? Since this is a homogeneous system, it is enough to check the rank of the matrix A alone. Okay, so it is, this matrix is equivalent to 1, 1, 2 and this is 1, sorry, 2, 3. Okay, so this is going to be 1, 2, 3, sorry, this is 0, right? These entries are 0. So it is going to be 0, 1, 2, 0, 0. It is 4 minus 1, sorry, 4 minus 3, which is going to be 1. Right? Here the rank is 3. Therefore, it is a linearly independent set. Okay. What happens in the second? Instead of 6, we have 7 here, right? So when we have 7 here, it is the change that is happening. So it is 7 minus 3 is going to be what? 4. And here you are just multiplying it by 2 and then subtracting it. So you have it to be 0, which means you are getting the rank to be 2. Hence, it is not a linearly independent set. Right? So here you have linearly dependent. If this is linearly dependent, some entries are independent and some entry can be written as a multiple of a, sorry, that is the linear combination of a previous entries. Let us try to do that too. Okay. So just for the convenience purpose, actually I have given you the entries in the arrangement form. Here let me try these two things, whether they are linearly independent or not. Let me try that. So x times of 1, 1, 1 plus y times of 2, 3, 4 is equated to 0, 0, 0, and this is going to give me x plus 2y, x plus 3y and x plus 4y. So this implies what? X plus 2y is 0. When x plus 2y is 0, this, upon substitution in these two entries, it is going to give what? Y is 0. If y is 0, this implies x is 0. Therefore, it is linearly independent. Or you may try with the help of the matrix idea as well. So this is going to 1, 2, 1, 3, 1, 4. It is to be multiplied with x and y and it is to be equated to 0, 0. Okay. Here the number of unknowns is 2. The maximum rank of this matrix can be 2. If it is 2, then it has a unique solution, which means your given vectors are linearly independent. Here it is happening. Therefore, it is linearly independent. Now we may try. This can be. We can write this as the linear combination of these two entries. So if that is the case, what? We are some linear combination of this is equated to 3, 5 and 7. Okay. Now it is we can find the values of x and y such that it is happening. Okay. It is going to be what? X plus 2y, x plus 3y and x plus 4y. It is to be equated to 3, 5 and 7. Okay. So this gives you x plus 2y is 3. So if you substitute x plus 2y is 3 in this, what? X plus 2y plus y is 5. This is 3 plus y is 5, which means y is 2. If you substitute y is equal to 2 in this or in this, you will get the value x plus 4 times of y, it is 8 is 7, which means x is minus 1. You can substitute the value of x and y in anything and you can check. So this 3, 5, 7 can be written as minus 1 times of 1, 1, 1 plus 2 times of 2, 3, 4. This is your 3, 5, 7. So the theorem is verified for these vectors. Now let us check for the third case. Hope you have seen the previous lectures, so that in those lectures we have proved this collection to be linearly dependent one, and we have just now proved this collection is a linearly independent collection. Therefore this can be written as a linear combination of these entries. Supposing I try this, okay, x times of 1, 1, 1 plus y times of 2, 3, 4 plus z times of 3, 5, 6 is equated to 11, 12 and 13, right? So this is going to give me what? X plus 2y plus 3z, x plus 3y plus 5z, x plus 4y plus 6z, and is equated to 11, 12 and 13, right? So when I try to this is now you are getting what? You are getting a non-homogeneous system of 3 equations with 3 unknowns. So if you write the augmented matrix, you will have these things, right? Now let us try to find out the equivalent matrices of this thing to find out rank. What I am actually doing here is I am trying to find out the solution of the given system using rank method, and hope you people have studied rank method in schoolings. Okay. So I have to do here to write. Here from this I can see that rank of AB is same as that of rank of A, which is same as that of the number of unknowns. Therefore I am going to have a unique solution, and from that I can deduce Z to be 0 and Y to be 1. So if I substitute Y to be 1 and my X is going to be 9, right? So this is happening. So these are the unique values for this case. Suppose in this example itself I am changing the things, that is, instead of this 6 I have 7. What is going to be the case? I am going to have this is only these two are linearly independent. This can be written as a linear combination of these two things. How are we going to write this as a linear combination of these two things? That we have seen just before in this. Okay. In addition to this, we have one more thing. This also can be written as a linear combination of these two things, which means I will not have this part. Okay. If you just equate, you will have x plus 2y is 11, x plus 3y is 12, okay, and x plus 4y is 13. Substituting x plus 2y is 11 in this, you will get y to be equal to 1. If you substitute y is equal to 1 here, you will have x is 9. Okay, so 9 times of this plus 1 times of this gives you this. Okay, if you are writing with the help of these three, okay, In order to differentiate only, I have used different colors. If you are writing with the help of these three things, these two alone gives you this. Okay, whenever we write it as a linear combination, it is not necessary that we have to make use of all the entries. Sometimes the chosen scalar may be 0 as well. Right? Hope in this lecture you have got the idea of the theorem and how to make use of the theorem to verify these things and all. If you have any queries, you can post it in the comment section. That will be clarified within 24 hours of time. Thank you for watching.